This section, we are putting everything together. I'm going to give you a function. You're going to find the first derivative and the second derivative. We're going to make one giant chart. Here's what we need to find always. The domain. If we have fractions or for square roots, figure out the domain. If it's not negative infinity, positive infinity, take the bottom set equals 0, take the inside set greater than equals 0. Kind of have an idea what that domain is before you get started, because you don't need to be making a graph or a chart if you don't have a graph there. Find the vertical, horizontal asymptotes, and then we're going to do x, y, y prime stuff, right? Increasing, decreasing, relative, extrema. We're going to find inflection points. We're going to find where it's concave up, concave down. So any extrema, asymptotes, extrema, maximums, and inflection points, all on the chart, all on the graph, all right? Find the intercepts if they're easy to do so. So this is our very first function. I'm going to show you how to do this and this together. What you could do is pause the video real quick and you could practice finding your first derivative and your second derivative. Couple of quotient rules with your factoring. Got to be able to get those down on our own. So practice those if you need to. And then what I'm going to do is start right here with those derivatives. And we're going to practice doing the chart together and the graph together and get these skills down without the calculator. All right. So if I have my first and second derivative, you set the top and the bottom equal to 0. And I'm getting these three like critical numbers that we're going to check to the left and to the right of. All right. So we're going to make one giant x, y, y prime, y double prime chart. Bunch of space here. And we're going to throw in all of these numbers on our chart. We've got to get the exact x's if I'm asking for maximums and inflection points, but the decimals are helpful when we're putting them on the graph there. So we want to have kind of both there. So the first one we're going to do is the negative square root of 7/3. Leave a little space, going to throw in the 0. Leave a little space, and the positive square root of 7/3. And then leave a little space there. I actually didn't need this last line. That's kind of bugging me a little bit there. Just kind of like ignore that. But a little space to the left and to the right of each one. And then what we're going to do is we're going to do the first derivative stuff first. Sorry about that. So first derivative stuff first. Just look at the x equals 0. I'm going to put a 0 in right here. And what I'm going to do is go ahead and circle that. And all my increasing, decreasing maximums is going to be based off of this. So I just need something over here, right? Notice I don't have any zeros or undefined to the rest of it. So I just need to do like a -1 and a positive 1. Remember, this is really -1.53, positive 1.53. So I just need to take both of those numbers, something to the left and to the right of 0, and plug in this to the first derivative. That bottom is always being squared, so I really just got to plug into the top. So if I plug in a -1 to the top, that's giving me a negative number right there. And then everything to the left of that's going to be negative. If I plug in a positive 1 to the top, that gives me a positive number right there. And everything's going to be positive. So we know that means our function goes decreasing, increasing. So if I go downhill, then uphill, that's going to make this a relative min. So if you have any relative max or min, you got to find those y values, put them on your chart, put them on your graph, right? So when I plug the 0 for the original function, 0 divided by 7 does give me 0. And that's the intercepts as well. If you want to plug in the 0 for x and y and find the x and y intercepts there. And then I'm going to do the second derivative. This is where the top is equal to 0. So I'm going to put in zeros right there. That's where the second derivative is 0. And then you can use your different colors here. Just be as neat with these as possible. I'm going to use a different color. And usually for the second derivative, I'll put this like in a rectangle. So my first derivative, I'm always doing like ovals. And then the second derivative, I like to do the rectangles there, and it's kind of easy for me to keep track of. Sometimes you'll have an oval and a rectangle, and then you got to check to the left, right. So now when I'm checking the second derivative row, I don't care about the circle stuff right now. I just look in between the rectangles. I need to check something here, one thing in between, and then something over here. So I'm going to have to choose -2. I'm actually, since I don't have a 0 or undefined here, I'm going to choose 0. Now, if I had a 0 undefined there, I would also have a rectangle right there. Then I would need to use the -1, the positive 1, as my test points there, and I can use a +2 right here as a test point there. So if we plug these into, remember, this is your second derivative row, plug it into the second derivative. Now, normally, when I'm cubing it, I got to plug it in right there, but I know the denominator, since that's being squared, that's 0 or positive, and then you're adding to it. So this part, this inside part is going to be always positive, then you're cubing it. So this whole denominator is going to be positive for us. The 14 is always positive. So really the only part that I have to plug in is right there. So if I plug in the 2 and the negative 2, you're going to get 7 minus 3 times 4. You're going to get 7 minus 12. You're going to get negative for the negative 2, negative for the positive 2. If you plug a 0 in for that x right there, you get a positive number. So everything in between there is going to be positive. So remember, this tells us concave down, concave up, concave down again, which means if your second derivative changes sign, your original graph is going to change concavity, which makes both of those points inflection points. So I usually just kind of label those as inflection points, which means you need to find the y values, put them in your chart, put them on the graph there. So if I take both of those numbers, plug those in place for x, I'm going to get 1/4 for both of those. And remember, it's okay to get the decimal answers for the y's. You got to have the exact x's if we ever ask for what is the inflection point, but it's okay to get decimals for the y's. But that was not a huge deal to plug those radicals in, square them, and get some nice numbers right there. All right, now here's the easy part. This should hopefully be the easy part. The hardest part of these is going to be finding that second derivative. Sometimes those second derivatives get a little bit crazy, and then it's a little bit rough sometimes there. So we'll have some work there to kind of support you with that. And then sometimes the charts get a little bit tedious there, but it's not really too bad. It's just, arithmetic doing the signs. And now we're going to do the graph, just like we did before. If you have any intercepts, if you have any asymptotes, put those on your graph right there. So I kind of mentioned right here initially that the domain is all real numbers. That denominator is never equal to 0. There's no vertical asymptotes there. That bottom is never equal to 0. And the horizontal asymptote is at y equals 1. So I'm going to get y equals 1 as the horizontal asymptote. And then if you have any points, put the points on the graph right now. You got 0, 0 is a min. You don't have to do this, but I like to put little m for the min, capital M for the max, and then I for the inflection points there. So then we're going to go negative 1.53 and then up 1/4. So I'm going to have like an inflection point about right there, and then another positive 1.53 up 1/4. So I'm going to have another inflection point about right there. So I got those 3 points that I found. Those have to be found, have to be on the chart there. So this is kind of a pretty advanced method of graphing here. You don't need to make a bunch of XY charts. You don't need a bunch of points. We just need the most important points in the asymptotes, and we're going to have our graph here. Now, pay attention to this part, last part here. You're looking at the signs here. First derivative and second derivative, right? Remember, and you're just going to translate this, all right? First derivative negative, that means your function is decreasing. Second derivative negative, that means your graph is concave down. So from negative infinity up into that very first dot that I have down, I got to draw something that's going downhill and also spilling water. So we're going to go decreasing, concave down like that. Now in between this point and this point, that's in between your rectangle and your oval here, you're looking at the sign, the first derivative and the second derivative there. You're decreasing, concave up. So you got to make it go downhill and then concave up, holding the water. Now your derivative is equal to 0 there, so it should be smooth and curvy, not a corner point. And then you're in between the min and the inflection point. That's in between the oval and the rectangle, increasing, concave up. So you draw something that's increasing, concave up. And then it goes on the other side of that all the way to infinity. We're increasing, concave down. So you're going to make that increasing, concave down. Done. Let's review how to find a slant asymptote. A slant asymptote occurs when the degree of the numerator is exactly 1 larger than the degree of the denominator. So something like this, x squared over x, or x to the 4th over x cubed. And then long division will always work. Now, if you have a linear factor like this, synthetic division will work a little bit quicker, and you're welcome to use that. But long division always works, because if I have an x to the 4th over x cubed, I can't use a synthetic division. You can only use synthetic division if it's a linear function. So I'm going to review long division once. Guess what? We're going to need long division in the future when we do integrals later on. So I'm going to review this once, and that's it. And if you have other questions, you're going to have to ask about those individually, because you're supposed to know this. You should have been doing this since you're like freshman in algebra 1 here, or you guys took down like the 8th grade or something like that, all right? So here's what you do when you do the long division. To find the slant asymptote, you look at the first 2 things in both of them, like x. You're thinking x times what gives me 2x squared? That's going to be a 2x. You then take that 2x, distribute it, times it by the x minus 2. So that's going to be 2x squared minus 4x. And then you're subtracting the stuff, and then the shortcut we gave you before was just switch your signs. Make that a minus, make that a plus. Just switch the signs right there. Those will cancel out. This will be a negative x plus 5 carries down. Now, you're not done with the long division until this degree right here is smaller than this degree right here. So since they are both x to the first, the same degree, you got to keep going and you just do that process over again. You look at the very first things in both of them. You're thinking x times what gives me a negative x? That's a negative 1. So you throw that up there, then you take the negative 1, you distribute it through that x minus 2, so you can get a negative x plus 2, and then switch your signs, make that a minus, make that a plus, make this a minus. Those will cancel out. 5 minus 2 gives you a 3 for the remainder. When you're finding the slant asymptote, this is your slant asymptote right here. My y equals 2x minus 1. That's how you find the slant asymptote. You throw the remainder away. If you're wondering why we throw that remainder away, remember how we had you write these last year? You would write 2x minus 1 and you put plus 3 over x minus 2. It's just like if you take 4 into 9, you're going to get, like 2 1/4, right? You just put plus the remainder over the divisor right there. Now, remember what a slant asymptote, that acts like a horizontal asymptote. Remember the definition of a horizontal asymptote is a limit as x approaches infinity. So like the slant asymptote will act the same way as a horizontal asymptote. It's going to approach that slanted line as you approach infinity. Now, if I do the limit as x approaches infinity here, see, you got this 2x minus 1 guy, but then look what happens when you plug in infinity right there. So that's going to be like 3 over a billion, 3 over a trillion. That part as you're approaching infinity is going to go to 0. And then that's what you're left with right there. And that's the graph of that line. And so you just graph that line, like make it dotted, there's your slant asymptote there. All right, we are going to do one more example. And I already got some of this stuff filled in just to make the video a little bit shorter. But here's what I'm going to do. I'm going to give you a function. And then right here, you could pause and kind of practice this on your own. That's a pretty intense, first and second derivative right there. I did quotient rule, did some factoring. Actually, I did that with the simple. I just distributed and then did a little bit of factoring there. And then I did another quotient rule and then some major factoring and then got my second derivative there, right? So you can pause the video and get those down or try those on your own, especially if you kind of struggle with derivatives in the past. We got to make sure we handle those right now. Those don't go away, right? So you got your first and second derivative right there. And I'm just going to show you again how to do the chart and how to do a graph there. So if you think you got it from the last example, just go ahead and start that homework there and see what you can do with it. If you want to pay attention to one more problem, that's all we got here for us, all right? So I did find the vertical asymptote, set the bottom equal to 0. The degree on the top is larger, so no horizontal asymptotes, but you have a slant asymptote. So I already did that long division there. I got y equals x as a slant asymptote. And so you can even put those on the graph right away. You got a graph here. You can go x equals 2 and negative 2 as the vertical asymptotes. And then you got y equals x as your, my fault. There's a graph there. You got your vertical asymptotes. Then you got the y equals x as your slant asymptote. So 0, 0, 1, 1, 2, 2. Slant asymptote is going to be going like this. All right, so we got those on there. And then from the first derivative, you got these critical numbers to try. There's a bunch of them, and I threw those on the chart for you already. And then from the second derivative, you got these numbers to try. So you got to put all those numbers all in the chart, left to right in order. And now let's do just the first derivative at once. So I put, like, if it was up from the top, it was 0, the bottom was undefined. And I also put undefined for the asymptotes right there. And let's do the first derivative part together, okay? So this was about negative 3.46. This was 3.46. That's kind of helpful to know those decimals. And let's choose stuff to the left and to the right there. So I'm gonna go negative 4, negative 3, negative 1, 1, 3, and 4. So they get a little bit lengthy sometimes, a little bit tedious sometimes, but it's not like difficult. It's just, you just gotta plug it in and do that work. Now, when you look at the first derivative, this is being squared, which means it's always positive. This is being squared, which means it's always positive. So when I'm plugging in, I really only need to do the x squared minus 12 and plug it in right there. So if I plug in the 4 and the negative 4, I get 16 minus 12, which is a positive. So I get a positive there, I get a positive there. If I plug in a 3 and a negative 3, I get 9 minus 12, which is a negative there and a negative there. If I plug in 1 and negative 1, I get 1 minus 12, which is another negative there and a negative there. And so remember when I told you the signs don't always flip? It just depends on the function. There's a lot of crazy stuff out there, but just check those numbers each time and you won't ever go wrong, all right? And so that's gonna tell us increasing, decreasing, then it stays decreasing, and then decreasing, increasing. So if it goes up and goes down, that's going to be a max, a relative max. If it goes down and goes up, that's going to be a relative min. And then the signs don't switch here. So, but it's always important to check it on each side of that asymptote, because you know your function could easily change from going up to going down on each side of that asymptote there. That's why we always check that in the chart. All right, so then I'm going to define these y values. So you're going to take those x's, plug them into the original function. Remember what we said, it's okay to get the decimal answers for the y. So just plug that in the calculator. Got your y values there. And so those are the max and mins that you could even put on the graph. And so that's going to be like 3.46, and you're going to go up to like 5.2 or something like that. All right, so then there I have a min. And then we got the negative 3.46, negative 5.2. Right there, we're going to have a max. And then let's do the second derivative now. So the second derivative, I'm going to get a different color here, and I'm going to look at where I have the zeros and undefineds there. So I'm going to put rectangles around there. And I just need to do something to the left and to the right of those numbers only. And so you can use just the -3 as your test point. You got to use the -1 and the +1 in between, and then just the +3 as your test point. So I'm just going to tell you on this one, I think you know how to do it. You got to take it, now that's being cubed in as a -6, you got to plug it into the bottom. You got to plug it in right there. This part's always kind of positive there, but you really got to plug it into that 8x part, and that, because it's x squared plus 12, that's always positive. So I'm just going to tell you what these signs are. You just got to force yourself to do that. This goes minus, plus, minus, and plus. So they can alternate, but they don't have to, right? So just be careful on that. And then you're just going to go left to right. So you have your points on there. If you didn't have the points, also, your second derivative changed from minus to plus here. Now, technically, that's not an inflection point. It changes inflection, changes concavity, but it's not an inflection point because it's not an actual point there. It's just an asymptote. But we needed that because we're going to graph this whole entire thing, right? And we're going to know that the shape changes shape. The curve changes shape on each side of that. But see here, you actually have a point. You go from concave up to concave down. And this, when you plug 0 into the original function, you're going to get 0 for that y value. So at 0, 0, we have an inflection point. And now we're ready to do the graph here, okay? So let me try and squeeze in, zoom out a little bit so we can see the whole thing here. All right, so we're increasing concave down. So I'm going to draw something that's increasing concave down. And then in between that point and that asymptote, that's in between this point and this asymptote, we're decreasing concave down. And you see you got a max right there, so it helps you to know you're decreasing concave down like that. And then in between the asymptote and the inflection point, that's in between the asymptote and the inflection point, you're decreasing concave up. So I got to draw something like this, decreasing concave up. And on the other side of that, you're decreasing concave down. And in between the asymptote and the point, that's right here, you're decreasing concave up. And then you're increasing concave up. And then we're done. So please just practice doing those derivatives. We're going to have some support for the derivatives if you need some help with those, but you got to make sure you're practicing that on your own. I would rather us not messing up this part just because your derivatives off there. So it's really important to get those derivatives right and then practice all this stuff and just make sure we know that properties. The more we can practice these properties, watch when we do our AP review, they're going to give us the graph of the first and second derivative sometimes and ask us information about the original function, the first derivative, second derivative, and they'll ask us to do a bunch of different stuff. There is one problem where it doesn't give you a single fraction. It gives you a couple things kind of broken up, like with the fraction. What I suggest you do there is get a single fraction. Get yourself a common denominator single fraction first. And that way, when you do you could tell that there's a horizontal asymptote there or a slant asymptote there. Just kind of keep that in mind. We'll provide some work here for you to hopefully help yourselves and figure that stuff out. And then just be responsible with that. Use that responsibly. Use it to help yourself, and then get everything done. And then we could just go through a couple things here and there when we go over questions here. Thank you.